Hello and welcome back to my channel. Today I am going to continue building the Lone Star project in .NET 10. This is going to be the second part of the series. So if you have not watched the first video yet, I highly recommend you to go ahead and do that first. So if you are watching this series for the first time, I'm building a project called Lone Star, which is a simple browser game, and I'm also integrating machine learning in this project. Uh, I have maintained a to-do list for this project, and if you see, I have already completed the first part of this task, that is to train the binary classifier model. And I trained the model in a .NET file app, which was a single .NET file named trainmodel.cs. So there was a blunder in the video. So when we trained the binary classifier model, I had said that we can use any data frame when training the model, but that was technically incorrect. We should use the train data. uh, I mean that is the reason why we did the train test split, and we have to separate data set, train data and test data. So when we are training the model, we should always use the train data, and when we are testing to get the metrics and validate the model, we should use the test data. But I have already corrected this and uploaded the code in a GitHub repository as well. I will upload the link to the repository in the description. I encourage you to go ahead and take a look. And in addition to that, I have also made some other enhancements in the script. The first thing I did was to merge all the for each loops into a single one. So there were, I think, 3 for each loops which are now merged into a single one. And then when we were handling missing values for the categorical columns, I was doing one additional for loop where I was going through each row and making the change to the values. But now I have just done a simple reassignment to the column, which I think reads better. And I have also done something similar for the status column as well. So we created a new column, and then we had removed that column from the data frame and then added the new one. But now I have just done a simple reassignment, which I think is more readable and probably better for performance as well. And then one last thing that to I want you to notice is this one, where I have saved the process data, and this is before we do anything related to training the model. Even before we do the train test split, I have saved whatever we have done, like handling the missing values, deleting the irrelevant columns and all. I have saved that as process data.csv. And we are going to start the second task of this project, that is to create a synthetically generated data from this CSV file. Okay, so to create a synthetic data generator, I'm going to start in a new file. So let me just close this one. I will create a new file in the project directory, and this is going to be let's just generate data, and this is going to be a Jupyter notebook. I will explain the reason in just a little bit. Okay, let me just minimize this. Okay, so if you notice here, I have a Jupyter notebook, but if you notice, the runtime is .NET Interactive. So let me just give you a little background on what .NET Interactive is and why I chose this for this task. Okay, so .NET Interactive is similar to the file-based app, but the advantage is we can just see the output of the code that we write very immediately, and in addition to that, we can also have beautiful charts and markdown in it. So it's very similar to Jupyter notebooks, but instead of the language being Python, we can write the code in .NET. So that is the only difference. And to replicate what I have in my IDE, that is Visual Studio Code, you should have this extension installed, poly.notebooks. So if you have this extension installed, then you can go ahead and create the Jupyter notebook. But even though this is a Jupyter notebook, we will not be writing any Python code. We will be still working with .NET. Okay, so with that being said, the first task that we are going to do is obviously to install the NuGet packages. Okay, and the first package that we are going to use is obviously Microsoft Data Analysis, which is to load the process data. If you remember, I just mentioned we are going to use the process data from the first part of this video. And we are also going to use plotly.net because I'm going to have some charts done in this video, so that is the reason why I chose .NET Interactive. And obviously we are also going to need Microsoft.ml NuGet package to actually make some predictions. We will see by making the default predictions on the synthetic data that we generate. Okay, so how do we add these NuGet packages in a .NET Interactive file? Well, we do what we did in the we will do similar to what we did in the first part of this video. Let me go to the NuGet.org website, and let's see what packages that I have listed here. The first one is Microsoft Data Analysis, Microsoft.data.analysis. We installed this package in the first part of this series as well. So there we used file-based app because I was doing file-based app in that video, but now we are doing a .NET Interactive. So I'm just going to go ahead and copy this syntax, go to my code, and I will start a new code cell and then paste it here. So this is going to install the Microsoft Data Analysis package, and I'll also do something similar for the other packages that we need. Let me just copy and paste the code here. Okay, so this is Microsoft Data Analysis, this is Microsoft ML, which we are already familiar with, and I have also added one other dependency, Plotly. Let me just give you a quick background on that as well. So Plotly is just a plotting library that will enable us to see beautiful charts. It was actually originally intended to be used with F#, which is a functional equivalent of and functional paradigm equivalent of C#, but they have recently ported it to be used in C# as well, and especially in the interactive environments. So that is the reason I'm using Plotly, and actually just for the sake of these charts I'm using Plotly and also .NET Interactive. Okay, so with that being said, I think we are ready to execute this cell block. Let me just do control enter at the same time, or we can also just run it from here. This is weird. Okay, so the issue is I actually forgot to include one of the references. So to use plotly.net, we actually also need to have this one, the plotly.net itself. Okay, so let me just go ahead and add the reference here. Okay, so with that being done, we are ready to use these packages and build the project now. Okay, so the first thing that we are going to do after this is to load the data. Okay, now we are going to do whatever we have done in the first video, just using Microsoft Data Analysis. We are going to load the process data this time, not the original data, and we are going to load it in the data frame. Just name it data frame. Okay, and then actually if you remember, we are just trying to generate the synthetic data here, and we don't want to generate data for two columns for status, because this is the prediction level, and we want the machine learning model to predict status based on the generated data. We don't want to generate the status column itself, and we also don't want to generate the LTV column, which is loan amount divided by property value. So I'm just going to go ahead and exclude these columns from the data frame, just so we don't have any confusion later. Okay, so I have an array named skip columns because we are going to skip these, and for these skip columns I'm going to just remove those from the data frame. Let me just execute this. Oh, and I don't have the data. Let me see. Yeah, I don't have the data. I made the changes here, but I have not executed this. Let me just go ahead and do it. .NET train model dot cs. Okay, so that is done. Let me just close this. Now I have the process data CSV file. Let me go back and run this cell. Okay, and we have the data frame here, nice and ready. So this is one advantage of using .NET Interactive notebooks, because we can see this data frame nicely formatted and all. If this was done in the console, for example, then we would need to format this data ourselves. So we can just use this display extension method to get this nicely formatted data frame, and this will actually be very useful once we start plotting some things. Okay, now let's move to the next part, which is to convert the A's. So if you see, most of these are already numeric columns, but A's and reason are categorical, and we are going to generate the synthetic data using what is called a cumulative distribution function, and that works pretty well with numeric values. And we will also need to write separate code for categorical and numeric columns if we are to plot the charts. For that reasons, I'm going to convert these age and reason columns to numeric values, but this is not going to be as elaborate as one-hot encoding that we did in the first video. This is just going to be very light compared to that. Okay, so I'm going to just go ahead and then copy the code that I have written for it. But before we do that, let's see the logic behind it. Okay, so the Okay, so the way that I'm going to do this is first see the unique values, which I can do it this way. So there is this extension method on data frame columns called cast, which will just convert whatever values we have in the data frame, that will just convert it to a specific type. If you remember, we did this by using the age cast and then doing something like this in the first video, string data frame column, but I think this reads much better than that. So I'm just going to go ahead with this syntax, and for this I'm just going to take the distinct values and I'm just going to display those. So with the display we can get the result in the cell. So I'm just going to do the same for the reason column as well. So now how we are going to convert this to numeric is by using these distinct values. So for the age, what I'm going to do is, if it's less than 25, I'm going to give the average age for that, and which I think is 20, based on the size of the bins that we have here. For 25 to 34 it's 30, and then for 35 to 44 it's going to be 40, and so on. And for the regions, south, north, central and northeast, I'm just going to go ahead and assign a value of 0, 1, 2, 3. So this is similar to one hot encoding, but it's going to be very light compared to that, because we are not converting these to vectors and all. Let's just see how this looks. Okay, so we have converted the age and the reason columns to numeric. So if you remember, single data frame column is nothing but a data frame column which holds float values. So single is just another name for the float data type. So what we have done is, for the age we have used this pattern matching, and anything less than 25 is going to be matched to 20, 25 to 34 is going to be matched to 30, and so on. This is just the average age for the category that we are trying to map to numeric values. And in the data frame I have just done a simple reassignment. I just took whatever values we got from mapping each age onto to their numeric counterparts, and I just assigned those numeric values to the new string data frame column, which is assigned back to the data frame age column. So now the age is numeric, and similarly I have done the same for reason columns. Let's just quickly see what we have in the data frame here. I'll just see the first 10 values. Oh, I think we already did this once. That's the reason it's getting angry at us. Yeah, okay. So if you see, the age has been converted to numeric values, and the reason has also been converted to numeric values. So if you see, the reason here is 4, and we have mapped south region to 4. And if you look before we convert, the reason for the first row is south. Okay, so this is simple mapping to make our lives easier. Okay, and the next thing that I'm going to do is plot some charts. Okay, so we are going to see what is called a histogram for each of the columns. Okay, and for that I'm going to use plotly dot net dot c sharp. So if you remember, I already told you plotly was originally made for f sharp. So we have to use plotly dot net dot c sharp if we are going to use the c sharp syntax. Okay, so what I'm going to do is, for each column in the data frame dot columns, I'm going to use this chart class. Okay, and we have a method called histogram, which is going to plot the histogram. And now, for some strange reason, we should give the data type of the series that we are going to pass here. So if you see, it says x type, y type, and for some reason we also have to pass the text type. And in our case, the x type is going to be float, because we are going to pass whatever the series, whatever values we have here for loan amount, rate of interest, and so on. So this is the reason why I converted the age and reason columns to numeric, because if we had string and float, then we had to write this code 2 times, once for numeric columns and then again for categorical columns. So that's now we have all the columns is numeric. I can just go ahead and do it at once. This is the type of the series that we pass in this to plot the histogram. And then for the other y type, this does not matter for histogram, so I'm just going to give a string. And obviously the text type would be string. I don't even know why we need to pass that. Okay, and in the chart, the first thing that I'm going to pass is x series, which is going to be created from the column itself, because remember, we are looking through every columns in the data frame. And I'm just going to cast them to float values. Okay, so I think this will work. Actually, I don't think we need to even create this new object here. And then I'm going to pass something called his norm, which is going to take these values, take the exact numerical values, and we want to convert them into percentage to see what percentage of values does these individual points in the data take. Okay, so for that I'm going to use something called style param dot hist norm dot, and I have the options, many options here. I'm going to use percent. Okay, and then we also obviously need to display this. But before displaying, I want to add the name of the column that we are plotting, which is just going to be the column dot name. Okay, and then we get an error. uh, 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 oh oh, we need the version 6, sorry. So we have installed for plotly net interactive, we have installed the version 6, so this also has to be version 6. Okay, so we already have version 6. Let me just version 5 installed. Let me just restart the kernel. Okay, so this is equivalent to cleaning the project. Which is weird. Actually, let's just go ahead and see what the latest version of plotly.net is available in the NuGet. Oh, we have the preview version. Perfect. Oh, I have the preview version here as well. Okay. Now it should be good to go. Oh, we don't have the data frame because we restarted the kernel. Uh, okay. I don't think we need to run this. We need to run this. And hopefully this will work. Oh, it does not. Okay, yeah, we need to create the optional thing. So this can get quite frustrating, creating all these new kinds of objects just to plot some charts, but I can only say this is worth it. And here also we need to probably create something. Oh, we need to actually give the types here as well. Yep, as frustrating as it can get. Okay, so finally we have the histograms ready. So I mean, in this video I actually want to focus more on these charts and the reason why I'm creating the synthetic data this way more than the code, because the code, to be frank with you, I don't like how this plotly.net is structured for C#. So I'm not going to describe. I mean, I'm not going to explain this part in great details, but these charts are very helpful. Okay, so for example, if you see the histogram of loan amount, we can see that like only 3% of the total data is uh, this one. The mode has only 3%, and we have a lot of values, but there are quite a few outliers in millions. But most of the values are within 1 million, and the main thing that I want you to focus on right now is the shape of this curve, because we want to match this later. For the synthetic data also we want to match this distribution. That is the reason why we are going to use what is called a cumulative distribution function. Similarly, for the rate of interest, we have a peak here for one particular value. uh, Let me see if I can show you this one. I cannot, so it's very small, so very difficult to focus on this exact peak, but I think this is 3.99 because that was the mode when we calculated in the first video. And for the upfront charges also, most of these are zero. uh, Although this says minus 50 to 50, most of these are zero, and there are quite a few outliers. And then for the tom, so most of these are 360, like 80% of those are 360, and we have some other values as well, so this is also very skewed. Mm-hmm. And for property value also we have a skew here, so there is a peak which is like 12% with 308,000. And income also we have a peak, but this one is uniformly distributed. Credit score, so this is uniformly distributed, as you can see from the histogram. And age, okay, so 50 is the mode age here, so most of the records we have the age of 50, and I think this is for unknown, 0 is for unknown. Yep, so it's very less, like less than 1%, 0.1%. And then the reason, okay, yeah, so this is the last one, debt to income ratio. Okay, so these are the histograms which actually reflect on how this data is distributed across different columns. Now when we are generating the cumulative distribution function, okay, it's important to note the histogram as well. So what is cumulative distribution function? Cumulative distribution function actually derives from the frequencies of the data. Okay, so I'll just give one very simple example. Let's say I have two columns in the data frame x and y. Actually, let me just make this lowercase. Let's say I have x1. Actually, let's just see one series only. Okay, so let's say I have a series 1 2 3, okay, 1 1 1 2 2 2 2 2 3 3 4 4 and 5 5 5. Okay, yeah, let's just go ahead and go ahead with this data. So for this data I can create what is called a frequency table. Okay, I'll just say x and f. So this is exactly what we did for the value counts in the first video. So this you can, from the .NET point of the code point of view, this is the just, and this is just the value counts data frame, but in from statistics point of view, we will call this a frequency table. Okay, so this is same as the frequency table. Okay, and this frequency table is exactly what is being plotted as histograms in these charts. Okay, so let's say I want to get the frequency table for this series here. So what are the unique values first? 1 2 3 and then 4 and then 5. Okay, and what is the frequency for 1? Well, we have 3 ones, so this is going to be 3. And what is the frequency for 2? 1 2 3 4 5, so this is going to be 5. And for 3 it's just going to be 2. For 4 it's going to be 2, and for 5 it's going to be 4. Okay, so for every unique values in the series we have the frequencies of those values, that is just the count of how many times they have occurred in the series so far. And from the frequency we can create what is called a cumulative frequency. Okay, it's called CF in short. Okay, cumulative frequency, which is nothing but just the sum of all the frequencies before this data, when the values are ordered in ascending order. So these are sorted in ascending order, so I can just go ahead and maintain a sum of all the frequencies before this record, which for the first one is going to be 0, and for the second one it's just going to be the value of the first one. Okay, and then actually, okay, no, sorry, so it's also going to include this row. So for the first one it's just going to be 3. For the second it's just it's going to be 3 plus 5, which is 8. And for this one it's going to be 8 plus 2, which is 10. And then for this it's going to be 10 plus 2, which is 12. And for this it's going to be 12 plus 4, which is 16. Let me quickly see if this is correct. 1 2 3 4. Let's just sum this up. 5 6 7 8 9 10. Yeah, 10 plus 6 16. Okay, so this is how we are going to create the cumulative frequency table. Okay, now this is our cumulative frequency table, and the cumulative distribution function, okay, is just a mathematical function that describes this cumulative frequency. Okay, so 3 8 10 12 and 16, these are cumulative frequencies. And we can actually convert this to density. Okay, so let's just call these probabilities. Okay, so if we can convert these to probabilities, which is just going to be like the cumulative frequencies divided by the maximum total. So for this one it's going to be 3 out of 16, and for this it's going to be 8 out of 16, which is just 1 by 2. For this it's going to be 10 by 16, which is 5 by 8. And for this it's going to be 12 by 16, which is 3 by 4. For this it's going to be 16 by 16, which is just 1. So what does this probability mean? So for, let's say, for the x equals to 2, okay, for x equals to 2, so there is a probability of 1 by 2. What does that mean? Is that the probability that if you choose one value from this series is random, actually not this very series, but the population that this sample represents. So if you take a random value from that population, you have a 50% chance of getting a value that is less than or equal to 2. Okay, so that is what this probabilities mean. Okay, so the I'll just say CDF of 2, okay, equals to, what is the CDF 2 from here? 1 by 2, that is 50%. Okay, so this means the probability of the random variable x, okay, being, let me just make it capital to signify that this is the population, not the sample. So the probability of the random variable x being less than or equal to 2 is 50%. Okay, now if we see for let's say 4, okay, for 4 it's going to be 3 by 4, which is like 75%. Then the probability of the random variable being less than or equal to 4 is going to be 75%. Okay, now if you see for 5, obviously every value that we have here are less than 5, so the probability of the random variable being less than or equal to 5 is going to be 100%. So this is why we are going to use these probabilities, because if we are interested in like generating the synthetic data, then this is, I think, the this is a statistically robust way of doing that. So we are going to use this approach. We are going to calculate the cumulative distributions, and we are also going to calculate these probabilities, and we are going to see how we can use these probabilities to generate the synthetic data. Okay, so now it's time to actually implement this cumulative distribution function in code. And instead of having these comments, I'm actually going to write the actual code that we do. Now, remember we have calculated these probabilities for only one series of values. So this also has to be done for each column in the data frame. In data frame dot columns. Okay, so the first thing that we need is the frequency table, that is this x and f, which is nothing but the value counts data frame. So I'm just going to calculate that first. Column dot value counts. Okay, and we need to order by values. Why? Because if you remember, in the when we are doing this cumulative frequency calculation, the probability actually means something, right? So the probability means that, let's say for 4, if the probability is 75%, this means that the probability of this random variable being less than or equal to 4, right, like less than or equal to 4, is 75%. So this implies two things for us. The first thing is the x series has to be numeric, right? So this is the reason why we converted the A's and reason columns to numeric values. Now these are numerics. And the other thing is, in the frequency table, this series has to be sorted in ascending order, okay, by values. So actually we can say that this is values. Let's not disturb this, just name it here. So x is values and f is counts, okay, in our value counts data frame. Okay, so we have sorted by the values here. Now I'm just going to convert all the counts to an array, which will make sense a little later. And I'm just going to cast them to, I think, long. Okay, and I'm also going to have total counts, the total count, which is nothing but the sum of this. Okay, so the reason I have these counts as a separate array is to calculate these probabilities. So if you remember, if you see, not remember, if you see, actually we need these cumulative frequencies just to calculate the probabilities. So here I'm just going to go ahead and calculate the probabilities directly. These are going to be float, because if you see that, you can see that these are fractions. So let's just call it probabilities, and I'm going to calculate the probabilities from these counts. Okay, and how I'm going to do that is by using what is called an enumerable dot range. So this will just quickly give us data of type enumerable, and we will have the range in it. So we will obviously start from 0, and for each counts. Okay, so this counts means all these frequencies here, and for each index. Okay, so for let me just add one more row here, not here, actually just here. I'll just call this index. Okay, and this is going to be 0, this is going to be 1, this is going to be 2, this is going to be 3, and this is going to be 4. So when we are calculating cumulative frequency, okay, let's say for index 3, then what we can do is we can sum all these frequencies up to the third index, right? So 3, 5, 2, 2, which is going to give this 12 value for us. So this enumerable range 0 to constant length, okay, which will just give us this index array. The index all the indices is an enumerable here. Okay, now for each of this index, okay, I'll just call this index. So for each of this index, what I'm going to do is I'm going to select from the counts. Okay, so counts means frequencies, remember. So I'm going to select everything on the frequencies array up to that index. So for third index, I'm going to select everything up to the third index. I mean for index being third. So how can we do that? We can do that using the spread syntax very easily. From 0 to, it has to be index plus 1 because this is exclusive. So for this I am going to calculate the sum. Okay, now this is going to be the cumulative frequency, and we have to divide it by the maximum I mean the total of the frequencies, which is the maximum value for cumulative frequency, which is nothing but the total count here. Okay, so total count. So this is going to give me the probability without any issue, but there is one major flaw here, which is purely programmatic and nothing to do with the statistics. Okay, so the flaw is this is going to be long value, right? And this is also going to be a long value. Now when we divide two long values, what happens is, let's just quickly see it in a new code cell. I'll just say long a equals to 100. Okay, and then long b equals to, let's say, 150. So when we do like a divided by b, okay, so the expected result would be something like 100 divided by 150, which is what is 100 divided by 150? I don't know what it has to be, something, right? So 0 point something, but let's see what we get. Yeah, we get 0 because these both are long values, and when we divide a long by another long, the expected result is also a long value. So whatever this is in let's say double or decimal or float value will be converted to 0. The trick to fix this is to multiply this with a float value, which is just 1 in our case, and we can see the exact value. Or we could also do a cast like this will also work, but I think it's better if we just go ahead and multiply with 1f. Okay, so this does it, this does the job. Now we have the probabilities here. Okay, so probabilities, we have the this thing in the probabilities array. Okay, but I want this in the data frame as well, in the value counts data frame. So let me just go ahead and do that quickly. Okay, now that's done. So now I have in the value counts data frame, I have 3 columns: values, counts, and I have added a new one called probabilities. Okay. Okay, so yeah, I think let's just see what we have in the value counts data frame first. Okay, and by the way, when we are using display even for large and large data frames, this in .NET Interactive we will get this nice little formatted view where we'll only see 25 rows at a time, and we can go to next page and navigate through. So I mean, for a lot of reasons, especially for data analytics, this .NET Interactive is very helpful. Okay, so we have the value counts, okay, which I think this one is for the first column, which is I think loan amount. So we have these probabilities. Now these are very low because we have a lot of unique values. I want you to focus on counts here. Okay, so let me just go ahead, and when we're displaying this, I'm going to order by okay, so yeah, let me just order by counts and then display this. Okay, so what I want to highlight here is like how many values we have which only occur one time in the data frame, and the main column that we are interested in when we are generating data synthetically are values and probabilities. Okay, now if you see, the probabilities are very similar for most of these values because they only occur one time. Okay, now the only reason why they would have different probability is um, if the cumulative frequency would be different, right? Because this probability derives directly from the cumulative frequency. But if the frequency itself is very low, okay, let's say for example we have 5 here. And then okay, so let's say for example if in case of instead of 2, if the frequency for the value 4 was, let's say 0, okay, just for the sake of argument, then this would be like 10 plus 0, and we would have 10 here, and then I mean the cumulative frequency is same for both of these, and instead of 16, I guess this would be um, 10 plus 4, 14, right? Then if you see the probability up to this point, like for 2 it's 5 by 8, and for 3 also it would be exactly 5 by 8. Why? Because this is still 10, and the total value actually totally changed now, so this has to be 14, and let's just make it 8 by 14. This is 10 by 14, and this is also 10 by 14. So you see the probabilities did not change just even a little bit from 3 to 4, right? And this is still going to be 1. So now when we are generating the data synthetically, okay, there is no point of having let's say this one, okay, in the table, because first of all it does not occur even once in the data, right? And right now this 3 and 4 are equally spaced, but let's say if this was like 3 and then 3.1, then it would not make much of a difference if we have 3 or 3.1. Okay, so why I'm trying to highlight this is because, okay, so let's see for the loan amount. So this one is like 1526,500 occurs one time. This also occurs one time, right? And there are so many other values. Okay, let's go to the last page. Like this one occurs 4610 times, right? So in comparison to this, these values have no significance, but we will still need the extreme value, because when we are generating the synthetic data, we want to make sure the whole range is covered. So we need the minimum value, we need the maximum value, and we need as much values as possible for the in between to preserve the this probability distribution. But for most of these, if they have similar value of probabilities, we are going to skip a few. Okay, actually we are going to skip a lot of these values. So now how do we do that? Okay, so how do we do that is actually not very straightforward. Okay, I'm going to make some changes here. Okay, so let's say we want to keep 20 rows. Okay, per column. So 20 rows means we will only have 20 unique values. Okay, let's just say unique values per column. So to do that, I'll just declare a variable max rows, and I will also have number of rows, which is nothing but value counts dot rows dot count. This is nothing but the count of unique values. Okay, and then now I want to based on the maximum rows, I want to create some indices. Okay, let's just call them like indices. Okay, and what this index is going to be, let's say if we have less than 20 columns, sorry, 20 unique values. So let's say if I have 5 unique values, then I don't want to disturb the distribution. I want all of these, which is in terms of indices. This is going to be this one, 0 1 2 3 4. I want every row, right? So I remember index just are I mean what the name suggests. They start from 0 and go up to n minus 1, and each row will increase the value of index by 1. So we need everything. But let's say if it is 28. Okay, then I cannot accommodate 28 indices. I just need to accommodate max 20. So what I'm going to do is I'm going to skip every row alternatively. So if I have 0th row, I'm going to skip to 2. Okay, so I'm going to go this way and all the way to 26. I can go it this way. Now after 26, when I skip one row, I should go to 28th index, right? But when I have 28 unique values, I will not have 28th row in the data frame. Instead, if I just skip that and have 26th index, then I will skip the extreme value, right? I'll skip the maximum one, because the maximum values, the extreme values are in 0th index and then in the last index. Why? Because we have sorted in ascending order by values. Okay, so after 26, okay, whatever be like it will be first I want to have the 20th index, even though it is like more than what I have in the data frame, and then I am going to replace this 28 with 27, because I want to have the first and the last. Okay, so now for this thing I'm going to maintain this index, and I'm going to do this only if the number of rows is greater than the max rows. Okay, so I'm going to do something here. Okay, so now how do I like skip? Okay, so to skip based on the values of max rows and number of rows, I'm going to first calculate what is the step that I need to have between two indices. Okay, so for 5 it's going to be 1, the step is going to be 1, and for 28 the step is going to be 2. But where are these values coming from? So 1 is nothing but just like if you see 1 is nothing but just it comes from 5 by 20, right? Because this is less than 1, we have incremented by 1, and this comes from nothing but 28 by 20. Actually, let's just do +1 here. I'll also do a +1 here. Yeah, now what we can do, instead of doing the +1, we can use the ceiling function. Okay, and then I can just say what are the number of rows I have divided by the max rows that I want, and it gets mad at me for some reason. Oh, so I need to just multiply it by 1. I have to convert this to float, and then the step is double, which I think is fine. And the next thing that I'm going to do is calculate the number of indices that I will have when using this step. So what is the number of indices that I'm going to have is obtained by again using the enumerable dot range. Now I'm going to go from all the way. Oh, sorry, these are the actual indices. So the number of rows is just going to be like yeah, they are just going to be, I think, not number of rows, sorry, number of indices, right? So for 28, when the index is 28, I'm going to have like 28 divided by two indexes here, right? So because I'm going to skip everyone, alternatively, every index alternatively, I'm just going to have 28 divided by 2. Okay, so if I just complete this, 6 and then 8, 10, 12, 14, 16, 18, 20, 22 and 24. So let's just count this: 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15. So it's just going to be one more, okay, which is obtained to ceiling, because when it's exact we don't need to actually add that extra value. So it's going to be number of rows divided by step. Okay, so okay, I hope this is making sense to you. Now we will calculate the exact index, which are coming from enumerable data range 0 to the number of indices we have here, right? And then for each of this index, okay, I'm now going to compute each of these element individually, elements of the array. So how do I do that? Well, for the, let's say this index is just like 2 times the index, which is 1. This is just like, sorry, this is 1 times the index, this is 2 times the index, this is 3 times the index, right? So it's just going to be index times step. Okay, so these are just the multiples of steps. And why is this angry with me? Oh, that's so the number of indices has to be int. This has to be an integer. Nah, let's just leave it var. And this is still angry with me because now I need to convert these into long. Okay, so oh, okay, so this is first we should no, I actually don't know why this is getting angry with me now. Cannot. I think let's just need to recompile. Oh, where is double here? I don't see any double. This is int. This is also int. Oh, step is double. Okay. Yeah. So index we don't need to do anything. Step we need to convert. Okay. Okay. Yeah. So this is just type errors that we need to take care of. That's okay. Okay, now that's done. Let's just include, we need to make sure that the last index is included, right? So if you see, when we did this for when the number of indices is when the max rows is 28. When we skipped skip the indices alternatively, we actually had 28 here, right? So we actually had 28, but then we forcefully converted that to 27. So that is what we are going to do here now. So the last, so this is how we can index backward. It has to be, what does it have to be? It has to be the maximum possible index, which is just number of rows minus 1. Okay, I think this is good except for one thing. I don't know if we should subtract 1 from here as well. Let's just see first. Yeah, okay, so now, oh, we still have so many rows. Why do we have so many rows? Oh, we just computed the indices but did not apply the filter. Let's just apply the filter. So I'm just going to reassign to the same data frame, but this time I'm going to filter with not the bool type. Yeah, I'm just going to filter by indices. Okay, so I'm going to have a primitive data, but I think these are longs. Yes, these are longs, and we don't need the name to be anything, but the values should be indices. Okay, so here we have only 20 rows, right? But the probability is still, oh, did we, what did we do? Why are these not in order? We have ordered by values. Oh, we have ordered by counts here. Let's remove this. Okay, so now this makes more sense. Okay, so we have the probabilities all the way from 0 to 1. Okay, so this is what we want, and we have 20 different values. That includes the minimum and the maximum as well. Okay, because if this was not the maximum, then the final probability would not be 1. Okay, let me just quickly show you how this works. Let me just comment this line here. I'm going to run the same code, and you can see now the final probability is 0.9999, which I mean not exactly 1, because this is not the maximum value that we can have. Okay, so we need to forcefully have the last index in the indices that we are going to choose. Okay, so this is the cumulative frequency table, okay, that we are going to use. So this is what we have here. We don't need this cumulative frequency. In fact, we don't need the frequency as well. So we will go ahead, we can even go ahead and remove the counts column, but it's okay, it does no harm. These values and probabilities are the main thing that are going to be useful when we are going to generate the synthetic data, and this is what we call by cumulative distribution function. Now, although we don't have the exact mathematical equation of the function, we have the empirical description of the function. Like we have one-to-one mapping from values to the probabilities, and that is also the reason why it's called empirical cumulative distribution function, empirical CDF, and that is what we are going to use. Now, if we are going to use that, right, so obviously we need to make that reusable. Okay, so for that reason, I am going to save these cumulative distribution functions for future use, especially when we are generating the data, because we have to generate the data from the application itself, from the game itself, not in the notebook. So for that reason, I'm going to save these in a JSON file. Okay, so let me have that here. And then this is just the I'm going to have the column name here. Okay, so this is just going to be in this format, like column name, and here I'm going to have the float values. Okay, so float let's just call it X, and here we are going to have the probabilities. Okay, so for each column I'm going to have this kind of structure saved as JSON. Okay, so for that, let me just, for each column, after I have calculated the value count here, I'm going to save that, okay, as a dictionary here, and the CDF values and CDF probabilities are nothing but the columns from the value counts data frame. Okay, so here I have first cast the values column to float values, and probabilities also in float values. These are just arrays, and starting from the CDF values array, I have zipped that into an array of tuples. This is what zip does: applies a specified function to the corresponding elements of two sequences, producing a sequence of the results. Okay, so it will give a tuple, and this is the tuple that we get from the value and then the probability. So we can reverse this. If we reverse this, the first would be probability and the second would be value. That's the only difference. And from here I'm just creating this anonymous object with value and probability, which I'm converting to dictionary although this says KV, these are not the key vaults actually. Sorry, not the key value pair, not key vault. So the key value pair, I'm extracting the value and sorry, the keys from the value. This may get confusing. And then the probability. Okay, so value means X, probability is the probability. These are the keys of the dictionary, and these are the values in the dictionary. Okay, and finally I'm going to save this as the JSON file. I'm just naming the JSON CDFs. Okay, and let's also serialize CDFs, which is the name of the variable. And to use file and JSON serializer, we need to have the using system.io for files and system.text.json for JSON. And also, instead of displaying these in as data frames, let's visualize these through some charts. I think that would be helpful. Okay. Oh, actually we have not added anything in the dictionary. How silly of me. So we need to actually add, right, this CDF in the dictionary that we are saving. Okay, so we have created a dictionary for the empirical cumulative distribution function. Okay, so this is empirical CDF for the column, and we have added that in the JSON that we are going to save with the column name. And this is just to visualize the CDF. I have plotted this is just a simple line chart. We give the X and Y values. I'm not going to go into too much details. Let's just run this and see. That is the cumulative distribution functions. So these are the usual shapes of what a CDF looks like. Okay, so for loan amount we have this CDF, right? And for the rate of interest also we have this CDF. So they have their unique shapes. Okay, they have their unique shapes, and all these shapes of the curves are actually derived from the histogram plots that we saw in the yeah, in this section. So for example, for DTIR, if you see the mode value is 37, right? Now if you see the equivalent CDF for DTIR1, which I think is in the very last. Okay, yeah, so for DT1 you can see a jump, right? You can see the sudden jump here from in that mode value. So the peak in the PDF corresponds to a rapid rise in the CDF. Okay, let me see if I can show that here. So for this CDF, the PDF would look something like this. Okay, the shape of PDF would look something like this. Okay, so if you are familiar with some calculus, then the derivative of CDF at any point, the derivative of the CDF would correspond to the value of the PDF. Okay, so this is the point distribution function. Okay, and this is the CDF, and CDF is just PDF is just the derivative of CDF. Okay, so this is what we are going to use. CDF is what we are going to use, and PDF is what we are going to compare our synthetic data to. Okay, so I hope this is helpful to you. Now the next step would be to actually create the synthetic data using the using these curves. Okay, using the CDF curves. So how we are going to use this cumulative distribution function to actually get the get the synthetic data? Yeah, I'm going to try to explain that using this curve. Okay, so the approach is to first generate the cumulative probability using a uniform distribution. So we'll just generate one value between 0 and 1 at random. Okay, and let's say I got the value of 0.7, then that 0.7 would probably correspond to one value of age here, right? So let's say this is okay, so this is like maybe something like 58 here. Okay, so I'm going to, in fact we are not going to like interpolate this. I'm going to just take the value that is just greater than this, which is just going to be 60 in our case, but you get the idea. So it may be like 58 here. Okay, I'll just write 58 here for 0.7. okay, now when we generate only one data, then this actually does may not make much sense. But let's say we are generating 100 different data points. Okay, so for 100 different data, we have a good chance of getting many values between, let's say, 20 and 70. Okay, so this is 70, so we have a good chance of getting many values between 20 and 70. Why? Because there is a good chance, right? So the 70, okay, this 70 corresponds to let's say 0.95 here. Okay, so 0.95, and then this 20 corresponds to something like 0.01, I would say. Okay, so in this case we have covered like the whole range of possible values from 0 and 1. So we have 0.98, so we have 98% probability of getting a value between 0.99 and 0.01, and in 98% of the cases we are going to have the age between 20 and 70. Okay, now let's narrow this down. Okay, so for example, what is the probability of getting the age between 0 and 20? It's just 0.01. okay, so the probability of getting the age between 0 and 20 is 1%. okay, now what about 20 to 40%? So 20 is like 0.01, and then 40, if you see, just corresponds to this point here, which I think is like 0.38. okay, I'm just making these values up, but you get the idea. So 0.38 minus 0.01 is 37%, right? So between 20 and 40, this range, we have a 37% chance of getting the value, the age between 20 and 40. okay, and similarly for 40 to 60, for 40 to 60, now 60 corresponds to this point here, which I would just say 0.81. okay, now 0.81 minus 0.38, right? So this is just going to be 0.57. okay, so we have a 57% chance. okay, and for 60 to 80, right, so 80 just 1, so it's just going to be 0.19. so sorry, so this is 19% chance. okay, now you see, so you see the difference of just generating a random value of age you see the difference of using the cumulative probability distribution, because when you use cumulative probability distribution, even for equal range of ages, we have different chances of getting those random values. Why? Because this curve is not a straight line. Okay, so based on the actual empirical distribution of the age, okay, we got this cumulative probability curve, and based on this curve, when we generate the random data, we have unequal chances of getting the different values of ages, and this will match. Okay, so for example, when we generate let's say 100 or 500, I mean, as the size of the random data set increases, it will match the actual empirical distribution that we had, which is the point distribution function. Okay, so this is how we are going to approach this. Okay, so let's just without wasting any more time, let's just go ahead and write the code to do that. So to generate so first let me just outline the steps. Okay, first we will generate the CDF value. So this is just a random value between 0 and 1, and then we will find the x value, I would say, from CDF that corresponds to CDF. Okay, this I don't say from CDF to the CDF value. Okay, so now we are going to have to do this n number of times. Okay, so let me just write the code for that, and we are going to need a random pseudo random number generator, which is provided by this random class. Okay. And we could just use the same CDF that we previously had, but I'm just going to go ahead and like pass from the actual JSON. Okay, so we already have that CDF, but I'm just going to go ahead and pass it from the JSON just to make sure that it's still working. So JSON serializer dot deserialize, and I'm going to give the type here dictionary of string, and here's the value. We are going to have another dictionary of floats. Okay, and what we are going to deserialize is the JSON in CDFs.json. And what's wrong with this now? Okay. Oh. Okay, so this is the CDFs that we have for each column, and then I'm just going to copy and paste the code for now. Okay, and I'm going to explain it later. So the number of observations that we are going to generate is 1000. I have chosen a very large number just to illustrate how these point distribution functions match, okay, for the synthetic data. And this synthetic data is just going to be a data frame. We are going to select every column from the CDFs, because remember, these strings in the dictionary are the column names, and we are going to create a column for each keys in the dictionary. Okay, so for each key in the dictionary, so the kv.key is the key of the dictionary, which corresponds to the column name. Okay, so kv.key corresponds to the column name, right? And then the kv.value has the dictionary in this format, right? So x and then probability. Okay, so for the probability, we are just going to generate it random. This is the first step, generate CDF value. Okay, let me just remove that from here and write it here, and then we are going to find the x value. Okay, we are going to find the x value that corresponds to the CDF value. Okay, and we are just going to take the first value that we find in the dictionary that we have created with which is just greater than the probability that we need. Okay, so this is how we are going to generate the random values. Okay, and this is going to be done for every column, right? So this is going to have all the synthetic data that we need. And by the way, we are doing this for the range of 0 to the number of observations. So in the column we will have an enumerable of number of observations length, so that means we have 1000 rows. Okay, now one important thing to notice here is I have assumed that each of these columns have independent distribution. Okay, now since I have excluded one column, that is loan to value, which was very evident to be derived from loan and the property value. Now there can be some indirect relationship between these columns as well. Okay, so for example, let's see, the credit score may have some relationship with the income. So for a particular income, it may be like empirically impossible for a different for a certain credit score. Okay, but that things are not being considered, which would actually be very complicated to consider like multivariate distribution functions. So for the purpose of our project, I have just assumed that all these columns are independent. Okay, so assumption here is all the columns are independent. Okay, or better even to say that they represent random independent random variables. Okay, okay, with that being said, now we have the synthetic data being generated. The important thing that I want to verify is the histogram, right? So I emphasized earlier that the whatever synthetic data we generate, it should match the empirical histograms that we have plotted. Okay, so let me just go ahead and run this code, and we will just see for a few of the histograms. Okay, so for that I'm going to duplicate this, and then let's see. Okay, so for loan amount, okay, so this is the empirical, I mean for the synthetic data, and for the actual data we have this one. So if you see, if this represents the population, right, then this very closely represents the sample we have generated. Okay, now the number of data points is very less because this has like millions, sorry, not millions, like hundreds of thousands of data, and this only have 1000 data. And if you see, the shape matches very closely. Okay, now note that this percentage are also skewed. Why? Because when there are many data points, a single data point actually corresponds to less percentage, but the mode is still the same. Okay, it's 206.5k for us. For this, it's 236.5k, so it's more or less the same. Similarly, if we see for let's see one more, and then we'll just call it a day. For rate of interest also, we have like a close resemblance of the population, that's just a population for this actual observed data set, and the synthetic data that we have generated. Okay, the peak here, the mode here is 4.025, and this is very hard to see, which I think is very close to 4. So this is the advantage that we get when we use a cumulative distribution function instead of just generating the data at random. Okay, now for the upfront charges also, this match is very closely, right? So it's like we are still using the real data, but we have the fresh data to play with. Okay, so I think this is the important part of this video. Okay, but there are still a few things that we need to do, which I'll just go through very quickly. Okay, so one important thing that we need to do is first let's just see the synthetic data. Okay, so we have a data frame 1000 rows, but the age and region are numeric, and we cannot just go ahead and use this data to make predictions using the machine learning model, because in the machine learning model, when we trained the data, we had this age and region as categorical columns, and we have done a lot of things like one-hot encoding, which does not apply to these categorical column. So for that reason, we are going to have to convert age and reason back to the categorical columns. Okay, I'm not going to go through the code for that. I'm just going to paste the code here, which is actually just a reverse of what we did earlier to convert the floats to strings, sorry, the strings to floats, and now we have converted the floats back to the strings. Okay, so it's just that. And one more thing we have done is we have computed the LTV. So whatever data we have generated for loan amount and property value, remember that LTV is dependent, like evidently dependent on these two other columns. So we have not independently generated this LTV, because there is one very important assumption that all these columns are independent when we generate synthetic data, but this is clearly not the case for LTV. So we did not generate LTV. But we need the LTV for to make the predictions. So we have derived the LTV in this way here. Okay, now this synthetic data is actually complete. Okay, now we have all the value we need to make the predictions. And making predictions using a machine learning model is also already covered in the first part of this video. So for that also, I'm just going to paste the code. Okay, now there is nothing fancy being done here. So we are just using the Microsoft ML package reference, then creating the ML context. So whatever we do with this from this namespace, we need to do it within a ML context. And we have loaded the model from the zip file which was created in the first part of the video. Okay, in the model. And remember, when we train, we use the fit method, and when we make the predictions, we use the transform method. So we are using the transform method on the synthetic data because this is the data we want to make predictions on. Okay, and I have generated what is called a gameplay data by making the transformation, by making the predictions. Okay, and then I have updated the status column because we don't have a status column here yet because no predictions was being done. And for the status column, I have just taken the gameplay data, converted it to, because it's just an I data view, I converted that to data frame for all the rows, because remember, to data frame by default only takes the first 100 rows. I have 1000 rows here, so I want all of those to be included. And the label which is predicted by this model is under this column. Okay, predicted label. So I have just taken the predicted label column from the model. Okay, from the predicted values, I have just taken this predicted label column and mapped that to the synthetic data status column. Okay, and here we are just going to see what the status column is predicted for these values. And just as a, I mean, this is not at all necessary, but I just wanted to see like what is the default rate. Okay, in our synthetic data, how many, I mean, what percentage of the data is defaulted. Okay, what percentage is defaulted? Because let's say if for the synthetic data, for some reason, if no loan is defaulted, then the gameplay is not going to be very interesting. And just for comparison, I'm going to do the same for the original data that we had. Okay, before we generated the synthetic data, let's see what we had. Yeah, I'm just going to see it right here. Okay, at the very beginning, just after loading the data, let's see what was the default rate. Okay, so the original default rate was 24.64%. Now because I have maintained the distribution of these variables, I have maintained through the cumulative distribution function, I have made sure that this remains more or less the same in our synthetic data. And because our model was, you know, considerably good, I expect that ratio to remain more or less the same. Okay, I'm just going to run all blocks once again, all cells, and the original rate was 24.64%. Let's see what we get for the synthetic data, and that will also mark the end of this video. Okay, so we got 32.8%, which is slightly larger than what I expected, but you know, it's still not that bad. Okay, let's just run it one more time. It does not matter that much, but I just wanted to verify. I mean, if it's something like 80%, you know, or let's say something very low like 7%, then we would need to worry about it, but it's more or less the same thing. So I think whatever we have done a pretty good job here. I will obviously add this code in the repository as well. You can take a look later. I hope I was able to explain all this at least moderately well. And obviously, so this is just the second task of the project. We have a lot of more things to do. Hopefully I'll see you in the next one. Thank you for watching. See you.